Welcome to this video lesson. In this video, we will be doing two practice questions on power and efficiency. In the first question, we got a motor which is lifting a block of 500 kilograms up at a constant acceleration. The block starts at rest, and 1 minute later, it's got a speed of 4 meters per second. Assuming that the efficiency of the motor is 40%, we need to determine the electrical power required for this task. Okay, let's talk about where the energy is coming from and where it's going to, and that will help us a little bit in understanding the question a little bit better. Well, I'm going to draw a diagram. We got a motor. Let's say this motor has some sort of pulley that's used to pull this box. This box is 500 kilograms, and the box is traveling upwards. So let's say it's got a velocity in that direction. And this is the motor, and the motor is plugged into the wall, and basically the power, the electrical energy, it's coming in and it's being transformed into other forms of energy. What is it being transformed to? Well, electricity here, some of it is being transformed into the work that the motor is doing to increase the kinetic energy and to, in this case, lift up. So that's EK, so that's EG. So these two are increasing. There's no force of resistance in this case, so there's no air resistance or anything. So in this case, we don't need to worry about that. And the other amount of energy from that electricity is going to waste. So I can either label this as W waste or E waste. And basically there's going to be sound in the motor itself. There's going to be heat. There's going to be radiation and other things, but there's going to be a whole bunch of energy that's being wasted. So let's draw a bar chart for this to give us a better idea about the energy transformation. So I'm going to include this, and let's say we got EK1, we got EG1, we got the W, and I'm going to include the W electricity in here, and that's going to, once we add these ones, it's going to equal to the kinetic energy 2 plus the gravitational energy 2. We're going to make an assumption, so I'll write that in. Assume negligible air resistance, meaning that there's going to be no frictional forces on the system here as it's coming up. And we're going to assume that air resistance here is so small that we're not going to include an E thermal here or energy loss due to any frictional forces of the block itself coming up. And plus E waste. Okay, let's look at the question again. It's being brought up at a constant acceleration. It starts at rest, meaning that kinetic energy at stage 1 is 0. And at the end, it's got some kinetic energy. I'll leave that in. So this is the initial kinetic energy. Here is also 0, so that blue is just the initial one. Gravitational, initially, let's say it starts at 0 gravitational, because we can just assume that our 0 point is when it's at rest, and that would mean that 0 here. And then we got the work here, which is the electricity that we're using, and that electricity is going to have certain amount of waste. So the efficiency of the system is 40%, meaning 40% will be useful energy. So I'll have about 40% here. I'm going to call that the energy that's going into the motor, or Wm, and the rest of it is going to be wasted. So this is going to be W. and this is going to be electricity. So basically, I am including everything in here just so that we get a better idea about what is happening with all of that electricity. We can see that part of it is going to waste and some of it is going to the motor. The amount that's going to waste, I'm just going to put it right here right away. And that's approximately this big. And the rest of it is going to do two things. It's the rest of it, which is the motor, all the useful energy, is going to change the kinetic energy and the gravitational. So with the pink, all of that pink, some of it is going to go here and some of it is going to go here. I don't know exactly how much at the moment, so I'm just going to draw it like this. So all of that electrical energy, some of it was wasted, the rest of it went to increasing the kinetic and gravitational energy. Okay, now we have a good idea about what's happening in terms of our energies. We know that the efficiency of the motor is 40%. We need the electrical power, so we kind of need to figure out what this value is, the work, and then use that to find the power. But in order to find this, we kind of need to find the work done by the motor and then use the 40% to find this. And to find the work done by the motor, I need to figure out the kinetic energy at stage 2 and the gravitational energy at stage 2. I have the velocity at stage 2, so I can use that to find the kinetic energy at stage 2, but I don't have the, let's see, the block starts at 1 minute. I don't have the height, but I do know that it's going at a constant acceleration, and as soon as I know that it's constant acceleration, I can use the equations of motion to figure out how far it's traveled. So let's start with energy equations actually, and I know that Wm, the pink here, all it's done is that it increased the kinetic energy and gravitational energy. So that's going to equal to the change in kinetic energy plus the change in gravitational energy. And since kinetic energy at stage 1 is 0, that's just EK2. And gravitational energy at stage 1 is 0, that's just EG2. And this is going to be 1/2 mass speed 2 squared plus mass g H2. I am going to use equations of motion, but I haven't done a very good job with my system diagram here. So I'm going to come up and draw that system diagram a little bit better. We got the motor, which is pulling this. It's going to be two different stages. The box is going to be here. Speed 2 is 4. And initially it was here. Speed 1 was 0. The displacement here from 1 to 2 is what I'm trying to find. The time it takes from 1 to 2 is 1 minute. I do need to change this to 60 seconds. And I don't know my acceleration value. I know it's constant, and therefore I know that I can use the equations of motion. And I'm going to take up to be positive, and meters, seconds, and kilograms, and my mass is 500 kilograms. Beautiful. Let us now see what information we have. We have initial velocity, final velocity, and time, and we need to find displacement. And the equation that I will use for that is displacement is equal to V1 plus V2 over 2 multiplied by delta t. And that's 4 plus 0 divided by 2, which is 2, multiplied by 60, and that will give me 120 meters is the total height from here to here. And assuming that it starts from height of 0, my final height 2 is going to equal to 120 meters here. Going back to my equation, I have 1/2. I have the mass. It's 500. My final velocity is 4 plus 500, 9.81, and height 2 is 120. And I can put this all in my calculator to get 5,92600 joules. Okay, this is good. I'm just going to go back and see the question again. So far so good. I have the work done by the motor. I can right now find the work done by the electricity right away because I have the 40%. And I know the amount of time it took for the whole process. That's 1 minute, and I can use that to find the power required. So let's do that. I know that efficiency is going to equal to the work done by the motor divided by so that's the useful energy divided by the input energy, which is from electricity. And that's going to equal to, and sorry, I'm going to rearrange for WE, which is going to become WM over the efficiency. Plug in my values. You always want to show the values plugged in as one of your steps. 0.4 for the efficiency. And I will end up getting 1481500 joules. That's the total amount of energy actually required by the electricity. A lot of it is going to waste, as you can see, but we get approximately 40% of that being used to lift up and give speed to our box. And the power that is needed by the electricity is equal to the work done by electricity over time, and that's 4,81500. The time it takes for this process is 60 seconds, and when I divide the two, I will get, I need to see the number of significant figures, so I'm going to go back up. 2 significant figures for time of 1 minute, giving me 25000, and this is watts. And that is my final answer that I will highlight. Note that what I could have done was to find the power of the motor first by dividing this by 60, and then use the equation that efficiency is equal to the power of the motor divided by power of electricity, which is power, useful power over input power. And that would have given me the same power. This is a lot of power, actually. This is saying that 25,000 joules of energy is being produced every second in order to make this happen. Kind of makes sense. It's a very heavy object, so that amount of energy probably makes sense. For our second question, we got the physics truck of mass 1200 kilograms with power of approximately 5.966 times 10 to the 5 watts traveling uphill. This is 800 horsepower. That's a lot of horsepower. Covering a distance of 500 meters and a height of 350 meters in 25 seconds. The car starts from rest and stops at top of the hill. Provided that the efficiency of this engine is 30%, determine the average frictional force acting between the tires and the road during this trip. Let's draw out the situation, and this time I'm going to do a little bit of a better job with my initial diagram. And we are going to have the truck. I'm going to kind of show it as a box. This is starting from rest, so speed 1 is equal to 0. And then it's going to reach the top of the hill here, so somewhere here, and speed 2 is going to also equal to 0 because it is still at rest. The height that it travels is 350 meters, so I'm going to call the displacement from 1 to 2 in the y direction is 350 meters. And basically the distance it travels, this distance here, in another direction, I'm just going to write distance from 1 to 2, no arrows, is 500 meters. Okay, good. And if you want, instead of this, you can just write this is the change in height. And that might actually make things a little bit easier. What else do we have? What else do we know? So we know velocity 1, velocity 2. We know the change in height. We know that kind of like the distance it travels. And it's going to be accelerating and then slowing. So it's going to speed up and slow down. That's the only way it can go from 0 to 0. So starts from 0 and kind of stop. It needs to speed up and slow down. So acceleration is definitely not constant in this case. What else do we know from this? So I'm going to assume that acceleration is in this direction, but it's not constant. And I know that it's not constant again because it speeds up to some speed in order to get up and then slow down to get to 0. And the time from 1 to 2 is equal to 25 seconds. My lowest number of significant figures, just so that I can keep it in mind for later, is 3 significant figures, so I need to leave my final answer in 3 significant figures. What are the forces acting in between? Well, there's the force caused by the engine. There's going to be a frictional force because that's what we're kind of trying to figure out. There's the normal force acting on it as it's traveling up, and there's the gravitational force also acting in this direction. And the engine force I've drawn a little bit bigger in this case because there's a component of gravitational force and frictional force, so they kind of add up. Maybe I've drawn it a little too big, so I'm going to replace that with something smaller. And here's the force diagram, so it kind of gives us an idea that the engine force needs to definitely overcome the force of friction, component of gravitational force in its way, and that's kind of it. All right, now that I have this set of information, I am going to go right ahead and draw an energy bar chart. Start at EK1 plus EG1. There's going to be some work done. The work is going to, let's draw this as the work of the chemical. So that's kind of like the energy that's coming in total. And let's solve this using this method. I'm going to call this W friction. And that's going to equal to the EK2 plus EG2 plus E waste. And that's the force, and so that's the energy that's being wasted. Initial kinetic energy and gravitational energy are 0. The chemical energy, that's a very large amount of energy. I'm going to draw this pretty big. And maybe I won't even color it in. I will start labeling it. So this is the chemical part. And you don't have to do this, but I like doing it because it helps me understand where the energy is going. So about 30% of this is going to go to the engine. So this is the fuel. 30% of it is going to go to the engine, and the 70% of it is going to go to waste. And I can right away include that wasted energy right here. So basically all of this waste is going down here. That engine force has to do a few things. In this particular case, from stage 0 to 1, the kinetic energy at stage 2 is same as kinetic energy at stage 1. So it's not contributing to the change in speed of the vehicle. However, it does two things. Something that it does, it has to overcome the force of friction. So there's going to be some loss of energy here, which I will draw. And the rest of it will be to increase the height of the car. So this is portion of this, and the rest of it goes in here. Note that this could be drawn differently. Maybe I'll draw the other model as well to kind of help you understand this. So it could be EK1 plus EG1 plus WC plus W. Instead of WF, force of friction, I am going to say is equal to EK2 plus EG2 plus E thermal 2 plus EW. It's the same idea. Kinetic energy, gravitational, kinetic energy at stage 2 are all 0. WC is going to be very large. Some of it is going to go to 30% of it is actually going to go to the engine. The rest of it is going to go to waste. So same thing, nothing has changed so far. But the other way you can draw this out is that a lot of it is going to go to gravitational, and the other one is going to overcome the force of friction. Now, let's write an equation for both of these cases and make sure that they will yield to the exact same thing. So WC, in the left-hand side, I'm not going to include WC and waste in my equation because they will cancel out. So I am going to just say that all of this chemical work, some of it is going to be wasted, and therefore WE plus WF, these are my works, and this is 0, 0. These two added together will equal to the change in kinetic energy and the change in gravitational energy. Change in kinetic energy in this case is 0. We know that already. We can go ahead and write this as the work in energy, as a work of the engine, which we don't have its value for, plus the work in friction, which we don't have its value for, is going to equal to the change in gravitational energy, which is going to be gravitational energy at stage 2 minus 1. And stage 2, we have some gravitational energy, but at stage 1, we don't have any, so I'm just going to write this out as mgh2. You can also just write it as mg delta h. The second way of writing this one, for this one, I'm going to write this one in maybe red. It's the same idea. All of this energy is going into these two, so I can write this as WE is equal to the change in kinetic energy, which is 0, plus the change in gravitational energy, plus, in this case, the change in thermal energy. And I'm going to get WE is equal to, again, mgh2 plus E thermal 2. All right, okay. So E thermal 2 and WF do have a relationship, and I will write it on the side here in case you forgot it. But a lot of times we use this relationship And this would make sense because if E thermal is negative WF, you can replace this with negative WF and bring it to the other side, and we'll get the it becomes a positive, and we pretty much have the exact same equation. But in this question so far, what do we need and what do we have? So we need the force of friction, average force of friction that's acting on it. And that would mean that I have to break this WF into force of friction and distance. So I'm going to do that in a second. And E thermal, we also kind of said in the class that we can use an equation for E thermal as distance multiplied by force of friction. So I'm going to do that on the right-hand side first. WE is equal to mgh2 plus E thermal, which is force of friction multiplied by the distance that is traveled. And on the right-hand side, I will use a different equation, WE plus or the work done by the engine plus the work done by friction is going to be the force of friction multiplied by the distance multiplied by the cosine of the angle between the displacement and the force, which is 180, and that's going to equal to mgh2. And I know that cosine of 180 is -1, so I will end up getting WE minus force of friction times displacement is equal to mgh2. Note that these two equations are exactly the same. In fact, I'm going to rearrange both for force of friction. So force of friction is going to equal to WE minus mgh2 divided by the distance. And same thing on this one. Force of friction is going to equal to, I'm going to subtract mgh2 from both sides and divide it by the distance. Exact same question. Obviously, doing the question properly using any method will yield you the proper answer. And in this case, I personally don't have any preference on whether you use this method or this method. All right, so we need the force of friction. We have the mass, we have the gravitational acceleration, we have height 2, we have the distance. What we need is the work of the engine. So I'm going to go back and figure out how we can find that set of information. So mass is 1200, power, oh, we got the power of the engine, and the power of the engine is same as the amount of chemical power that we can put in, and there's going to be inefficiencies in that. So I'm going to use this equation that power C is going to equal to WC over change in time. And also we know that the efficiency is 30%. So I'm going to use this equation to find WC. The amount of energy that the engine can use every second, which is what the power rating is there, is 596,600. Multiply that by the time, 25, and I will get 14915,000 joules. So that's the total amount of energy that will be used by the fuel over the 25-second period. And we want to see how much of this energy is actually going to the engine's ability to cause the change in gravitational energy and the change in the energy that is required to overcome the frictional force there. And to do this, I know that efficiency is going to equal to the work done by the engine divided by the inputs, WC. And if I were to rearrange this for WE, it would equal to WC multiplied by the efficiency. So that's 14915,000 times the efficiency, which is 30%, and that's going to equal to 4474500 joules. So that's the total amount of energy that's coming from the engine. Go back and plug all of those in, and it doesn't matter which, they're both the same equation in this case, so I'm just going to go back and write in black. Force of friction is equal to WE, which is 4474500 minus the mass, which was 1200, 9.81, and the height, which is 350. And I'm going to divide all of this by the distance traveled, which is 500. When I put all of that in my calculator, I get 708.6 newtons, and I can change that to 3 significant figures, and that's going to be 709 Newton is the average frictional force acting on between the tires and the car. So I'm going to zoom this out a little bit just so that all of the question is in. And let's just review what happened in here and what did we covered. So we had a 1200 vehicle going uphill, and it had to kind of overcome some gravitational force, and it had to overcome some frictional force, so the engine force needed to do that. No gain in speed, so it didn't really need to change its speed from beginning to the end. And basically the car is able to use this much energy per second or every second, and that's the input energy that goes into the engine. We're going to use C for that. And some of this is going to go to waste. That's the waste here. And some of it is going to go to the engine. And the engine force is going to overcome the frictional force and the components of gravitational force. In this case, that's acting against it. And you can see that here and here using this method, or here and here using the second method. Okay, once we have this, we can go and start solving the question. We could have just started with this part right away because we have the information about the power, the chemical power right away, or the input power. You can just use P in instead. And power chemical is equal to work chemical over change in time. Rearrange that, and we can see that in 25 seconds, the engine or the amount of chemical energy that's used up or inputted into the engine is very large right here. And we can use the efficiency equation to see how much of that energy actually is going to the engine in order for it to do useful work. And we find that out here. And once we have that, we will use the equations either from this or this. It will yield us the same answers. And let's just look at the second one here. The work done by the engine here is equal to gravitational plus, or change in gravitational plus change in thermal energy. Thermal energy is force of friction multiplied by delta D. Again, this is the thermal energy caused by force of friction between a surface and when it travels a certain distance. And then we just rearrange for what we need. We need force of friction, and we have the work done by the engine. We have the we have all the information to find the gravitational energy or the change in gravitational energy, and then we divide it by the distance, and it traveled 500 meters here, or 500 meters where the tire was in contact with the surface, and that gives us an average frictional force of 709 newtons.